Okay, how you doing? We're going to talk about simplifying some radicals with division properties. A couple things I want to point out very quickly. Important fact, headliner here, radicals may not be separated over sums and differences, meaning if you take a look at this radical I got going on here, I have a sum for my radicand, and my radicand says a squared plus b squared. So I'm taking the square root of that quantity. Now, it is extremely important that you understand that it is not equivalent to me being able to separate this and saying, let's just take the square root of a squared and then add to it just the square root of b squared. It is not the same, and if you want to test it, plug some numbers in and you will find that when you simplify it, that they will not be the same. So plug a number in for a, plug a number for b. Over here, plug the same a and b in, and you will find that they will never, ever, ever, ever simplify to be the same number. So it is extremely important, okay, that we understand this. So, next thing, the other important thing about roots, okay, we can only apply a root if our radicand is factored and the factor has a base with an exponent equivalent to the index of the radical. So, what I have here is that I've got some index of k, and what I'm showing here is factors, okay? I'm saying a and b. Anytime I show two things multiplying, they instantly are called factors. So, if I factor them and then this a can be written to some power of k that matches the index, then I can take that one and I can separate them out and I can take that one's particular square value and then I can multiply it by the other one. And the reason that we can do that is due to the wonderful product rule here. And the product rule states, okay, so let me pull this off here. The product rule states that I can allow this to occur where I have the a to the k times a times the same root b, then this occurs. And then we know, essentially, back going to what a square root is, that if I ever have a root with a radicand that has the exponent same, then it reduces to what just that base is. So, let's talk about some problems here. Let's talk about simplifying radicals with division properties. So, we've got this expression. And this expression says the square root of a squared plus 3a minus 4 divided by the square root of a plus 4. Great, that looks like a different language there. But we just have to come back to the idea of our division properties, okay, which states the quotient rule here. And the quotient rule, we notice here, says that if I have any radicals that have the same exact index, that I can rewrite them as taking this expression divided by the expression of the other. Now, the reason that we use this one, remember, all revolves around if they have common factors. Well, by this point, I would hope that you know how to factor an algebraic expression, and in this particular one, we have a quadratic expression divided by a binomial. So what I'm hoping is that when I factor this quadratic up here, that it is going to be they have a common factor of a plus 4, because if not, then I'm going to have a very messy problem. So, for our sake, I'm just hoping that it works. So here we go. What I'm going to do is utilize the quotient rule where I'm going to say, okay, let's write this all under one big roof. Okay, so here we go, where I have a squared plus 3a minus 4 all divided by a plus 4. And now what I'm going to do is I'm going to factor this expression, and when I factor that expression, I get the square root of a plus 4 times the quantity of a minus 1, all divided by a plus 4. And now we apply some basic rational root theorems, and the rational root theorem that I'm going to apply here is that if I have two factors that are being divided by a common factor, then I can go ahead and reduce those to a value of 1. And so what I'm left with for this final answer in this case is that I get left with the square root of a minus 1. That's not a plus, I meant to write a minus, it's plus Let me just get rid of that really quick. This is meant to be a minus 1. And that's my final answer. There's nothing more that I can do. It's an expression. We leave it as the expression, and we know that there's no more that we can do. Okay, on to example number 2. Example number 2 here, we're talking about cubic roots. So great, I have a cubic divided by a cubic, which then allows me to use this quotient rule. And the quotient rule has here that these indexes must match for me to apply this. And the only reason I want to apply this is that if my numerator, okay, the radicand in my numerator has some common factors as the radicand in my denominator. So here we go. Do they? And in this case, they do. I have a factor of x squared and a factor of x. These factors will have something in common, and I have y and y squared, so they'll have something in common. So I'm going to go ahead and break it into putting it all under one big radical sign. So I'm going to say the cubic root of x squared y divided by xy squared. Now when I reduce this, I have x squared over x, so applying some basic exponential properties that when you're dividing exponents through multiplication up here, that I can go ahead and subtract them. So this then becomes the cubic root, okay, of x divided by, and in this case, we're going to go ahead and reduce this, and y, 1 minus 2 is going to leave me with y. Now there's no more common factors, so what I must now do is break it apart, and I break it apart into the cubic root of x divided by the cubic root of y. Now, problem arises, and the problem that we have that arises here is that I cannot have a root in the denominator. So now what I must do is do something called rationalize the denominator. And what I'm going to do here is multiply by my magical power of 1. And the magical power of 1 that I'm going to multiply by in this case is going to be, what do I have to multiply this radicand by to make y cubed? Because if I make y cubed, then this radical then disappears. So I need to multiply this by the cubic root of, well, y times y squared makes y cubed. So multiply by y squared, and I multiply the numerator by this cubic root of y squared. And what I'm just simply left here with a final answer in this case is going to be the cubic root. Well, I can have the cubic root and a cubic root, so I can multiply these two radicands together, and I get the cubic root of x y squared divided by, well, this one here. Remember that if this radicand multiplied by this radicand completes it and the index then matches, that it is just the base. So in this case, it's a y. And then that's my final answer. So I hope that helps so far, and I hope I'm making some sense to you guys who are watching this. Alright, so let's go on to example 3. And example 3 says I have the square root of the quantity of x squared plus 4 divided by the radical of the square root of x squared minus 4. Now, this cannot be factored in the numerator, so x squared plus 4 cannot be factored. The denominator can be factored, but in this case it's not going to help me because it's going to be x plus 2 times x minus 2, and that is still not going to have anything in common with the numerator. So what I'm simply going to do here is I'm just going to apply the idea of rationalizing the denominator. So we go ahead and do this theory of multiplying by 1, and when I do that, what I need to do here is I need to create an expression that multiplies something that I have out here, two quantities of x squared minus 4 being multiplied together. If that were a 3, I would have to have 3 quantities being multiplied together. But in this case, because it's a 2, I only have to have 2 quantities. So I go ahead and I multiply top and bottom by the same exact radical. And when I do that, I multiply it by the square root of x squared minus 4. I multiply it by the square root of x squared minus 4. And then what I have here is for the denominator, now that I have 2 quantities of this amount, that radical disappears, and I'm left with simply on the bottom, that I'm left with x squared minus 4, and in the numerator, I'm left with the expression, well, I have the radical of x squared plus 4 times the square root of x squared minus 4. Well, x squared plus 4 and x squared minus 4, I hope you all do know that that is the same exact thing as having the square root of x to the 4th, minus 16. Now, it's important to understand that there's nothing more that I can really do. Because if I factor this, it breaks into these factors, and these factors, there's no common groups that will be the same. So therefore, I will not be able to do anything more. And lo and behold, my final answer is just this, this fraction. Notice that there is no radical in the denominator, though. So those are just working with some expressions. So let's start to put a little bit more numbers into it. So what I have here again is I've got the cubic root of 25y divided by the cubic root of 75x squared. I am going to apply the quotient rule where I can write these all under one roof because I have the same index, and I am dividing those radicals. So I'm going to write it like this, and the only reason I'm going to write it like this is because this quantity up here has a common factor as this quantity down here. It is not in the variables, but in this case it is in the actual numeric values of 25 and 75. So here we go. We break this apart, and we say that this is the cubic root of 25y divided by 75x squared. And from here we can then reduce the 25 and 75, which is going to be the cubic root of nothing I can do with this y, but this then becomes 3x squared. Now, I have no more terms that I can reduce or simplify, so what I'm going to do is I'm going to break it back. Okay, so I'm going to take this, and I'm going to put it back into something looking like this. So here we go. And then I'm just essentially just going back and forth between the two, that this becomes the cubic root of y divided by the cubic root of 3x squared. So, when I do this, the important thing to remember is that every factor for me to remove the root must match this index. So, as I bring this down here very quickly, I have the cubic root of y, remember, divided by the cubic root of 3x squared. Every exponent must match the index for me to get rid of the root. So, what I am going to multiply this one by, okay, the magical number 1 that I will be choosing in this case, is yes, it's going to have to be a cubic root. But if we notice, this is 3 to the 1st. So what do I have to multiply 3 to the 1st by to make 3 cubed? Well, I multiply it by 3 squared. Okay. And then this x squared, well, how do I make x squared into x cubed? Well, I multiply it by x to the 1st. And now each factor will sum up to being a cubic value. So, I multiply top and bottom by that because I am multiplying by 1 so that I don't change the value, but it changes the look. Up here, I'm just going to write what 3 squared is, which is 9. It makes no difference whether you do that or not, but this is going to be the cubic root of 9x. And when I finish this out, what I'm left with here is going to be the cubic root of 9xy divided by... Now remember that when I take the cubic root of this value, that it's just going to be the base, which is 3x. And there you go, lo and behold, we have it. A final answer is now produced. And that's the end of this video segment. So I hope that helps with division properties.